with Eric Swenson. And maybe I'll start with our motivation. So what is our motivation for this? Is characterize splittings, group splittings, geometrically. So what is the prototype of such a theorem is Bodich's theorem in the case of hyperbolic groups. Which says, so let G be one-ended, hyperbolic, not virtually surface group, then G splits over virtually Z over a two-ended group if and only if there is a pair of points that separates the boundary. So there are AB in the boundary of G such that the boundary minus AB is not connected. So since G is one-ended, we know that the boundary is connected, right? And now if we take two points out, it's not connected. This is how we can characterize splittings. And if you haven't thought about splittings before, you think I'm trying to confuse you. Yeah, I'm trying to confuse you. Surface groups split, right? You are not, you do, surface groups do split, but in all these theorems there is an exceptional case, one exceptional case, or two up to commensurability. So there are groups acting on the, say, on the hyperbolic plane or in the Euclidean plane with quotient the triangle, and these groups don't split, right? So there is no nice way to refer to them, and confusingly we say, oh, let's exclude surface groups. Well, surface groups split, but commensurable groups with surface groups don't split. So, okay, I don't know if I confused you more, but that's all I have to say about this. So basically, just ignore this, right? Just forget about it. That's the thing. We have a nice geometric characterization, right? A group splits if and only if a pair of points separate the boundary, and this is geometric. Maybe a final remark, well, this is really obvious, right? And the real theorem is this, right? Okay, so this part is an exercise, but the other part is the interesting part. And now, some time ago, we proved the same thing for CAT0 groups. So same is true for CAT0 groups. So again, you look at the boundary and they split over two-ended group if and only if a pair of points separate. But now this splitting theory, well, it's based on the JSJ theory, and of course what we generally understand, say, is splittings over Zn, right? So algebraically splittings over Zn are understood, and CAT0 groups, well, are more interesting, right? They have Zn subgroups. Okay, so how about splittings over, well, virtually Zn. Now, if you think a lot about something and you get stuck, well, then you call this thing a conjecture. So let me make a conjecture. Well, actually, I will attribute this to my co-author, Swenson. I won't admit I got stuck. So let G be a CAT0 group. And now assume G doesn't split over a two-ended group and well, and is not okay, G is not virtually pi 1 of S times Z times Z. Well, this, you better forget about this. So surface and a circle of its length to pi, or you can say finite if you're more optimistic, separates the boundary. Well, this is abusive notation, but I hope you know what I mean. Then the group splits over Z2, right? Then G splits over virtually Z2. So this seems to be a natural way to generalize the first theorem. And of course, one can be even more optimistic and go for every dimension, right? So replace this by Sn, and now let's say that with a teeth length, with a teeth metric is isometric to a standard Sn, right? And then ask that G splits over virtually Zk, where k is less than, or so let me just try that. You will say splits over something virtually Zk with k less or equal to n plus 1, right? So I don't even have to say it's one-ended or anything, right? So G one-ended, maybe I'll say it here. So this is a natural way to hope to generalize the previous theorem. And well, there is some evidence that there is a general a characterization of splitting, so a geometric characterization. So some evidence maybe for this is in manifold case due to results of Schroeder in the 90s plus the algebraic torus theorem of Dunwoody, Swenson. This implies that if we have a codimension 1 flat, right, so if there is a codimension 1 flat, in the universal cover of, so here it's a non-positively curved manifold, then pi n of m splits, well, over virtually z n minus 1, yes. Okay, so this is, well, this would be a stronger characterization, right? Just looking at the boundary, this just says, okay, if we have a flat that separates, then the group splits, right? That's again a geometric characterization, slightly weaker than this one, than this, well, but this is a theorem for manifolds, so this is a conjecture for groups.
You can find the non-positively curved setting?
Yes, only the non-positively curved setting, yeah, that's reasonable actually.
Sure, yeah, no.
So, but that's for Mn non-positively curved manifolds. Okay. So, well, but now let's go back and prove this conjecture. Well, there is something that might worry us, right? What if something smaller separates the boundary? We're here, right? So, question, what if something smaller than a circle, right, separates? So, for example, a finite set And this is related to a theorem of Bodice chain, so related to, so Bodice showed that if the boundary of G, so again G hyperbolic one-ended, has a local cut point, then G again splits over two-ended, right? So in fact we don't need a pair of points that separates even if we have a local cut point. So one can think, okay, maybe the same is true for cut 0 groups, except so again, well, how about cut 0? Well, this is easy, I can answer that. Doesn't make sense, right? Because just think Fn times set, right? The boundary of this is not locally connected. So if you like, every point is a local cut point, right? It's not even locally connected. But still, again, okay, so this doesn't quite make sense, but this makes sense, right? So we can still say, okay, let's forget about this local cut points. How about finite set of points, right? So it's what we could hope in this setting, right? What makes sense, right? So again, this question comes naturally, and this is what I'd like to talk about today. So a similar question. Suppose n points, well, greater than 2, separate boundary G, so G cut 0, one-ended. Well, not a surface group. Does G split over a two-ended group? And well, yeah, so this is true. This is what this talk is about. Yes, in this case we can prove it. And now note, this is of course the same. We can think of this as a purely topological fact rather than a splitting theorem, right? This says that if 2 points separate, if n points so this is equivalent to this, if n points separate the boundary of G, 2 points separate boundary of G, right? So it's a fact about the topology of the boundary, if you like. Okay, but now this is also related to some work of Guralnik. So he asked questions about that, similar to that, about convergence groups on continua, and one can use our techniques in this setting too. Okay, well, I assume everybody here knows what cut 0 is and boundaries and so on. So I'll just recall some things very quickly. So this part is boring. You can read your email. So so what is X is cut 0 if it's a proper geodesic metric space that has triangles thinner than Euclidean plane, right? So this is the definition of a cut 0 space, and now G is cut 0. So G is cut 0 if G acts on X geometrically. So this is what is a cut 0 group, a group that acts on a cut 0 space geometrically. And now this comparison condition allows us to define angles, right? So in cut 0 spaces, we may define angles So we can do geometry just using this comparison. So if I have 3 points, I can define the angle at this point, and also, well, the boundary of x is defined in the obvious way, right? So defined in obvious way. You just fix a base point and you take geodesic rays and the endpoints of the rays, define the boundary of x. So I was abusive before, right? When I say boundary of G, I just mean the boundary of this space x, right? So and now well, we have a topology, of course, as in the hyperbolic case, but now in this case you have some extra structure in the boundary. So, well, yeah, okay. So we get some extra. Structure in the boundary of x, right, which okay, so the Tits metric or Tits structure. So first of all, we can define the angle metric. Right, if we have 2 points A, B at the boundary, then we can take another point and take geodesics and look at this angle, the angle between AB with base x, and now we can define the angle metric. So we say that this angle is just the supremum over x of the angle between AB is this, and of course the angle takes values between 0 and pi, right? So and clearly, with respect to the angle metric, the action is by isometries, right? And now, using this metric, we can define the Tits metric. So, so the Tits metric is the path metric that comes from the angle metric. And we have some notation. So this is the Tits boundary. So that's the Tits boundary, which by definition is we take the boundary as a set, right? So here I forget the topology is a set, and I use the Tits metric here, right? So now some remarks. So it's a bit confusing. I would prefer to call it Tits structure because, well, the boundary of course is compact, but this is not generally compact. If you like boundaries to be compact, that's not a boundary. And well, but it has a nice property, right? The action of G on the Tits boundary, unlike the real boundary, is by isometry, so that's useful. And well, okay, maybe I'll draw some pictures. Okay, so it's so this metric of course gives a completely different topology, right? The usual boundary is compact. I mean the boundary is compact. Okay, maybe I'll just draw some examples. Well, maybe trivial examples. So in the case of the hyperbolic plane, the boundary, so this is x, then the boundary of x is a circle, but the Tits boundary now is just a bunch of points. And now with the angle metric, the distance is pi, and with the Tits metric, the distance between any 2 points is infinite, right? While if we take the Euclidean plane, then the boundary is a circle, and the Tits boundary is again a circle with the nice standard metric, right? So standard metric. So there is something unpleasant about the Tits boundary, that this is not even a metric, right? I said a metric, but actually this is a good case. So that's the crucial thing. if the teeth diameter is infinite, then the action is like in the hyperbolic, the action on the boundary is like in the hyperbolic case. We have north-south dynamics, we have three subgroups, and so on. So this is, I should say, a major unsolved problem in for cat0 groups, right? Whether teeth alternative holds, whether every cat0 group, which is non-abelian, not virtually abelian, contains a free subgroup, and when the teeth diameter is big, then this is easy. The same proof as in the hyperbolic case applies, but otherwise, so this bad picture is actually the good picture, right? This is the bad picture. Okay, so this is an idea about the boundary. Of course, in one direction the map is continuous, but in the other it's not. So maybe I'll say also that the identity map from the teeth boundary to the boundary is continuous, but of course not the other way, right? Okay, so this is okay. So why am I saying all this? Because of course I want to prove this theorem, so I want to look at the action of G. How am I going to prove it? I'm going to look at the action of G on the boundary. So how about the action on the boundary? So we have G acting on the boundary, right? And the action is, well, by homeomorphisms. But now let's take this example. So if we take Z2 acting on E2, well, the action on the boundary is trivial, right? So that's one problem. Trivial actions, well, even if the space is nice, if the action is trivial, you won't be able to prove much. So we need some tool, and okay. So in the hyperbolic case, of course, you know this doesn't happen, right? We have this north-south dynamics for the action, and you can do things with it. So here we have some weaker result, which we call pi convergence. So let me. So we call this pi convergence. So from convergence groups, that is. And now I'm just going to state a special case here that is closer to what. So what is the usual convergence action? You take a point x and you hit it by a sequence of elements Gn, and you converge. Well, you can pass to a point at infinity, right? So let's do the same thing. So let Gn be a sequence of elements in G and x in x, such that, well, we can always pass to a subsequence if Gn goes to infinity. So we can assume that Gnx converges to some point P, and Gn inverse x converges to a point N. So this is my P and my N, and I would like to have this attracting property. And now we don't quite have that, but then if the distance, the teeth distance of a point in the boundary from N is greater or equal to pi, then Gn of A does converge to P, right? So there is a bad neighborhood here, teeth neighborhood, right? So I'm using the teeth distance here, so there is a bad part where this dynamic doesn't apply, but if you're outside this part, if your A is here, you hit it by Gn, and then you end up here, right? So for big N, Gna goes close to P, okay? So we have some kind of convergence, but we need this. Okay, so we have some kind of action, and but now we want to prove
bigger than or equal to pi? It's really bigger than or equal to pi and not bigger than pi?
It's bigger than or equal, yeah, it works for pi. I mean, even in this case, right, you are up to there.
Yeah, silly. Yeah.
Oh, okay.
Yeah, just
Maybe
okay. Doesn't matter very much actually for what we do, but Okay, so now to get a splitting, we need a tree, right? So that's how we know to do these things. Well, we need a tree. So to get a splitting, we need an action on a tree. So here is our tree. We call it the cactus tree. Tree of a continuum. Well, let me just give a definition. A continuum. So a continuum is a compact connected metric space. So a continuum X is n thick if for every, maybe I'll call it Z not to confuse with my space, for every B subset of Z with cardinality of B less or equal to n minus 1, Z minus B is connected, and there exists an A subset of Z with n points such that Z minus A is not connected. And now we call A an n-cut. Okay. And now it's an old business in continua theory starting from the 30s, right? With Wyborn, 1930s. He explained, well, in modern terminology, he explained that if you have a cut point, then you can get from a continuum, well, he didn't call it an R3, maybe called it a dendrite or dendroid structure or something, but essentially he proved that, okay, if you have cut points, you get R3s out of your continuum, and if you have the action, of course, here, you get an action here. But now you're going to do the same. Of course, there is something that might be bothering you, which is that, well, cut points, of course, they have, I mean, it feels like they have a tree-like structure, but how about if you have bigger sets of points, like if you have a cut and another cut, well, they might be like that, and another cut might be like that, and where is the tree, right? Okay, well, so this is the central observation. Okay, maybe I'll write the theorem first, right? So this is the problem with cuts of more than one point, right, that they cross, okay? So let me write the theorem. Let X be an n thick continuum, then there is an R3 T encoding all n cuts of, it became again X, I don't know, maybe it will stay X, all n cuts of Z, okay? So, okay, so how can that be? Well, this is the central observation. I will just draw some pictures. I'm not going to say, I'm only going to draw a picture about this proof, or maybe two pictures. Well, the point is that the crossing sets are arranged in a nice structure, in something that we call a wheel, right? So philosophically, this seems to be a sort of JSJ theorem for metric spaces, right? Because this is what happens in JSJ. You have things in the second and straight way, but then, well, they form a ciphered fibered space or a surface, right? So it's a kind of JSJ theory at the zero-dimensional level. So crossing sets, crossing n cuts. So the central observation is the following: crossing n cuts are arranged in what we call wheels. And I will draw some wheels. Okay. So this is how your crossing end cuts might look like. So you see they are all arranged. So this is then equals to 4 case, right? And all your end cuts that cross just lie in a wheel like that. Or if you, or you might have something in the middle of the wheel. So, well, you could have several points here. I just draw. Okay. So this is n equals 3 case. And after you see that, you say, okay, I have these crossing wheels, crossing cuts, fine. I'll just say that this is one vertex of my tree, right? Okay, they'll just become this. The whole wheel gives you one vertex. And then, well, the technical machinery is, this is, I have a pre-tree that consists of wheels and cut points that don't cross anything, and then cuts. So we have either wheels of end cuts or end cuts that cross no other end cut. Right? We have these two objects, and there is a natural order on them called the pre-tree, and then you just join the dots of the pre-tree and you get your tree, right? So, but that's the whole point that of this.
Explain that picture back a bit more. So what's that slogan mean? Crossing end cuts are arranged in wheels.
What?
Can you just explain a bit more? What's that thing in quotes mean? Crossing end cuts are arranged in wheels.
Oh, okay. The quote was because I didn't define what is wheel, right? I just drew the picture.
But in those pictures, so what?
So the wheel, well, you see the wheel, but the wheel is. So the point is, you could think that you could have one cut and another cut like that, or I mean, when you cross, right? When you cross, maybe you cross and you go farther and farther, right? Right. This is what you are worried about, but this says this doesn't happen. You have something that cross, right? If you take something that cross, this is this. Well, now if I take something else that crosses this, I don't escape far away, right? I just say in this wheel, right? And this wheel has a cyclic structure. It's like a circle, right? This the cuts here. So if I take the half cuts, well, the half cuts. I mean this thing on the wheel is called half cut, right? So the half cuts on a wheel are arranged. They have a cyclic order on them, right? Okay, so if you had pair of points, I would just draw an.
Why is that one n equals 4 and that one?
Well, because this is not a cut, right? It's a half cut, right? So n equal to 4. That means so this is my continuum, right? The shaded part is the continuum, right? And now if I take 4 points, they separate, right? 3 points don't separate.
I hadn't understood. So it doesn't matter. It doesn't matter that you've drawn 6 of those. That's not the point. The point is.
No, in fact, generally we're going to have infinitely many things around here, right? It's just hard to draw infinitely many, right? But the central point is that these crossing cuts have a nice. They give you something like a circle, right? And you could have this middle part could have a finite set of points. And now, if you are in this picture, you have your cuts. So all the crossing cuts are going to share the same finite set here, right? Okay, and everything. So it's a bit surprising, not very hard to prove, I would say, but I mean, it takes some work to prove it, but the central thing is that this exists, right? That you do get this. So yeah. So if your continuum is separated by n points, then always you can get a tree out of it. You can, right? Well, of course, a tree. I mean, if this is all, yeah. If there are no other n cuts, you might get a single point, right? If this is exactly that. But usually you will get other stuff. I mean, you get cuts here and so on. So anyway, yeah. Okay. So. Well, there is a similar theorem. Actually, the reason of the name is that there is a similar theorem in graph theory about edge cuts. So, and this is a cactus. So, in graph theory, a graph that is made up by circles like that are joined in a tree-like fashion is called a cactus, right? So, the terminology comes from this cactus in graph theory, okay? Because we have circles. Okay. Okay, so we got a tree, but now we have to understand the action, right? So right, yeah. Sorry, I mean I didn't give formal definition. So is this clear now? Is it clearer? So what I'm saying is crossing cuts are nice. In fact, I mean they are all in a nice, right? So of course you would prefer them not to cross, but when they cross, they just give you these circles, right? Essentially, and you just say, okay, I take them all together instead of taking a single cut, right? So what you would like to say is you would like to say, okay, I have my cuts and I draw my tree, whatever, but now, well, instead of taking the cuts, you're going to take cuts and circles to draw your tree, right? That's how this works. So, okay, so G acts on the boundary of X, so this gives us an action on the cactus tree. But the problem is the action is by Homeo, and here, of course, the action is by Homeo. Okay, and so this is the same as what we saw in the talk on Wednesday, right? It's really an action by homeomorphisms on a dendrite, right? And this, as we saw, can be very bad. I mean, acting by homeomorphism on a dendrite well, doesn't help much. And now, well, of course, we know that if the action is non-nesting, right? So if T, so Levitt tells us if T acts on an R3T, so this is an R3, yeah. So by Homeo in a non-nesting way, then you can replace it with an action by isometries. Okay, good. Except not so good, because our convergence action is not so good, so we cannot do that. I mean, our action is nesting, right? But well, sometimes, I mean, if it is not nesting, then we use Levitt, right? But a priori, our action is nesting. So again, what does it mean to act by homeomorphisms? It's not, well, it is bad, but not too bad. I mean, what can happen really is that you have some interval, right? Or many intervals, okay? You have your element G that acts, and well, it might fix a part of the tree, and then on these intervals, well, the homomorphism acts by something like translation. It's conjugate to a translation, right? So this it acts as if these were R and these were translations, except it fixes the endpoints of this interval, right? So this is the bad nesting homomorphisms. This is how they look like, right? Okay. So this seems to be a natural thing to look at, right? You have an action by homeomorphisms on a space, so you're going to get an action by homeomorphisms on your tree. So, well, of course, again, the bad thing is that in general, you cannot say, oh, I shouldn't have erased that. Too late. Okay. Okay, so let me just give you an example of a nice, if this can be, example of a, well, nice nesting action. So nesting actions are not always bad, though. So let's say I have a group G that splits as F2. Okay, so let's say I have a splitting F2 ZG, some other group G. And now this is a graph of groups, and then I have the Basel tree of this splitting, and I see something like that, right? And F2 acts by rotating around this vertex. And now I'm going to go from this to a nesting action. Well, I'll blow this vertex, so this will become big, So I have f2, and now, well, let's say this is A. And now I'm going to replace this vertex by the Cayley graph, right? And now this element A is going to act hyperbolically on this Cayley graph, so I have an endpoint here. And now in this endpoint, I'm going to glue an edge, and this is another edge, and then I'm going to equivariantly extend, right? I have the action of my F2 here, so instead of being a rotation, it's going to be a real action on, and well, it's going to give me a countable set of endpoints of the tree, and there I can glue these things and then go on and so on. Now this thing is a tree, right? Okay, except the F2 elements act nestingly, right? So this is another tree, T prime, a tree, and these elements that were fixing a vertex now act nestingly here, okay? So, but this, okay, this is bad, I mean, but it's not too bad, right? Because it comes from an amalgam, right? So this is now, okay, so this is, so these actions are not, okay. Okay, so now what is the strategy for the proof? So, well, outline, unfortunately it's quite technical, so I cannot really, so there are 4 steps. So the first step is show G, the action of G on T does not fix a point. Well, second, show that G is rank 1. So the action on the boundary is as, say, a hyperbolic group action. So this is equivalent, in fact, to, well, this is not the definition, but it's equivalent to showing that the Tits diameter is infinite, right? So we have a big Tits diameter. And now, third, if the action of G on T is nesting, well, pass to a quotient tree, to a non-nesting quotient, to get a splitting. And if it's not nesting, so if not nesting, apply bus cell rips as we did in the n equal to 2 case, except, well, it becomes, this part also becomes more technical because you have more points and strange things happen again. So, well, let me try to say something about this. So to use this pi convergence theorem, you need some sets of big Tits diameter, right? So this is the first thing to note. So a remark or proposition. So if C subset of boundary X is a continuum, a subcontinuum separated by an n cut, or even by by at least 2 points. So if I have something like that, so this is my C, then this has big Tits radius. right? And now, as I have cut points there, it's possible to construct such subcontinua that have big Tits radius, right? So this is a geometric fact. And now, so let's go. So let's go to one, right? So there are three types of points: and cuts, wheels, and well, something, whatever is left, which I'll call just blobs, right? So now, if G fixes an n cut, then G virtually up to finite index fixes a point, and now there is a result by ρ1 that implies that G is equal to h times z, virtually equal to h times z, where h is many-ended, and we are done, right? Well, if we fix a point, then we have the splitting, and then of course h has to have many ends, otherwise we don't have finite cuts, and then we are done. Now, if we fix a wheel, we can use this proposition. So if we fix a wheel, there can be nothing in the center of the wheel, right? Because if we fix a wheel and the wheel has a center, then, well, the center is finite, right? It's a finite set of points. So again, we're going to fix a point. So the first thing is the wheel has no center, nothing in the center. So the wheel, so if we fix a wheel, if G fixes a wheel, W has no center. So we are in this situation, and it also is infinite. W is infinite, so it has infinitely many cuts for the same reason, right? Again by ρ1, both by ρ1. Okay. So we have infinitely many of these things here. But now what do we do? Well, we can create continua, subcontinua, like that, right? That have big Tits diameter. I can take one here and one here. And now, since I have infinitely many of those, I can find two. Well, of course, if the Tits diameter is big, I should say that. If we have big Tits diameter, then the dynamics is like in the hyperbolic case, so there is no problem, right? The problem is if we have small Tits diameter. But then I can find a gap between this part of the wheel, which has diameter less than epsilon. And now I can pick a P here and take a sequence of points Gn converging to this. Well, I can use pi convergence now. This continuum here is big, so there is a point here and a point here, which are both at distance bigger than pi from n. So both this continuum and this continuum have to converge in here, but they cannot fit in there, right? This is too small to contain both of those. Okay, so this gives me a contradiction. And now the blob case is more complicated, right? So again, having this big continua allows me to use pi convergence, and now I cannot pack them in there. Okay, so that shows, okay, so blob case harder, but again, you use similar ideas. You try to use this proposition and pi convergence. And now let's try to show that G is rank 1, so we really have a good action always. Okay, 2. G is rank 1, and what I'm going to show, so let's show the diameter of the Tits boundary is infinite. Okay, so let's say we have an n cut A, and we have an element. Well, we have no fixed points, right? So we know that we have elements acting hyperbolically. So maybe we have an element that takes A to GA. Well, this distance is going to be, say, epsilon. But now we repeat, and we have that its diameter is bigger than n epsilon, so it's infinite, right? Okay, good. Except, well, maybe G moves A, but this GA is not disjoint, right? So this is how we would prove it, except we might have a picture like that. So this is a nasty picture to draw. Oh, will I manage to draw this? So maybe these 2 points are always in common. So G acts like that, but there are these 2 points that are fixed, right? So I can say nothing about this diameter. So this is the picture in the boundary, right? And this is the picture on the tree, right? So I have my axis L of the hyperbolic element, right? So L is axis of G, but well, this whole axis gives me something finite in its diameter here, right? So it doesn't work. So somewhat surprisingly, a theorem that helps here is an algebraic theorem. So, well, we can use the following trick. So lemma by, well, this is a nice fact from the 70s. So let's say G acts on a set. So this is just a set, right? So a group G acting on a set without virtually fixing a point. So we have a group acting on a set without virtually fixing a point. Then for every A subset of omega finite, there exists an H in G such that H of A intersection A is empty, right? So, well, it's not very hard, but it's a nice factor, right? So if you virtually don't fix a point, you can take any finite set outside of itself. Okay, let's do this, right? We have this axis. Now let's take a set H, an element H, such that H of A, the same A here, is empty, right? Okay.
What does virtually fixing a point mean? Just as a point?
With a finite orbit, right? Or a finite index of group fixes it. It's the same thing, right? Okay, point with a finite orbit or a finite index of group fixing it. And now we have some element that takes this A to something disjoint. And now if you think what is the axis of HG, H inverse, it's going to be an axis because A and HA are disjoint. Well, you have to be a bit more careful than what I say, but because H and HJ, so if I call this element B, you're going to get an axis of an element B, right? So H of L, that is going to be disjoint from L. But now if I have these 2 axes, I can find, if I take GB, I think, or something like that, I can get an axis that goes like that, right? But now, if I have an axis like that, well, I just hit this by a sufficiently big power and I get to a disjoint cut, and I can apply the same argument I wanted to apply here, right? Okay, so this is, except, well, okay, so this is how you can do that, right? So again, if you just look at this element, just take a conjugate, the fact that this A moves to something disjoint from it means that the axis for this element B, right, for this conjugate is going to be disjoint from this, because everything in this axis will contain these 2 elements of A, right? Again, I'm cheating very slightly here, so, but that's true, right? So that's really true, but okay, so this works fine if you are in the non-nesting case. This proves rank 1. It's a bit more complicated if you are in the nesting case, because what might happen, right? So if you are in the nesting case, what might happen, but in nesting case, well, my axis didn't have to be all the way through, right? My axis could have been that, right? So this would be the axis L of G, right? If my G is nesting. And now when I try to produce a disjoint axis, maybe I fall here, right? So this is my axis of H of L for B, and this doesn't help. So you have to be more, you have to work more if you are in the nesting case. So this is Okay, but it can be done, and maybe I'll finish with what you do when you are nesting. So well, we prove some elementary things about nesting actions, so about the axis and so on. But the theorem is the following. Suppose a finitely generated group G acts minimally and nestingly, so there is a nesting element on an R3T with non-overlapping translation intervals. Then G splits over a stabilizer of an end of a cross component. So there are a lot of confusing terms here, non-overlapping translation intervals and cross components. Okay, so well, but you can imagine what I mean, right? So when we are nesting, we don't have real axes, we have just some intervals. So a nesting element might have some intervals where it acts by translation like that, right? So these are the translation intervals. And now what is the overlapping case? I might have a translation interval for G. Remember, these two are fixed. And now another translation interval which contains an endpoint of L. So this is not allowed, right? So we don't allow intervals of translation to overlap. So this is just about these finite intervals, right? We don't care about the real axis. And now a cross component. So a cross component is you just take translation intervals. So this is allowed to intersect, right? So you have a translation interval and another translation interval and another translation interval. Remember, you never go through the endpoints, right, when you cross, because this is not allowed. And now this is a cross component, right? So you squash, you collapse all these cross components, and then you get a new tree. And then, okay, so this doesn't finish it, of course. Then you have to control this action, right? So to really prove the theorem, you have to say more things about the end stabilizers and so on, that they're virtually Z. But that's how it goes. Thank you.
Are there any more questions? Do you believe the Swenson conjecture?
Seems reasonable. I mean, but I mean, the point of this talk is to explain. It seems hard, right? Because you have to do all this work just to find a set of points. It seems very reasonable, right? But that's why it's a conjecture.
Okay, let's thank Panos again. Come back in half an hour.